Hello everyone. I welcome everyone to this Power Electronics lecture series. So in the previous sessions, we started with the introduction. What is power electronics? Motivation on power electronics. So we started with a chopper. So after that, we derived a buck converter circuit and then boost converter, buck boost converter. For all these three converters, we derived output voltage equation and the design of L and C. We have seen the ripple current, the ripple voltage of the capacitor, ripple current of the inductor. So all these things we discussed in the previous video lectures. This is the detailed comparison of these buck converter, boost converter and buck boost converter. You can see buck converter where if you need a step down application, input voltage is high and I need the load voltage should be less than the input voltage, then you can go with a step down converter or buck boost converter. If you take a boost converter, mostly for renewable energy application, where the input voltage is less, but the load demands high voltage, there you can employ a boost converter. So buck boost converter, particularly for wide voltage range application. So it is you require, suppose input voltage is having some let me take an example 50. So your load may require sometimes above 50 volt, sometimes less than 50 volt. There you can employ a buck boost converter, particularly for wide range of voltage application. You are going to employ a buck boost converter. So if you see the output voltage polarity in case of buck converter, if I draw a simple block, let me take here input, here plus, here minus. So here the output voltage also remains in the same polarity, here positive, here negative. So there is no change in the polarity with respect to input. So the same positive and negative will be getting at the output side. For the boost converter also, it is going to happen in the same manner. So interestingly, we have seen in the buck boost converter, so where the output polarity gets reverse with respect to input polarity. So that is one of the concern it is there in the buck boost converter. And one more concern is the ripple current is going to be high at both input side and output side. If you just go through the buck boost converter circuit diagram, you can see one thing here. So let us draw the buck boost converter circuit diagram. So this is what we have seen in the previous sessions. So here inductor is present at the middle, and here there is a switch connected to the input side, and there is a diode here. So here capacitor connected across the load. So one thing you can observe here, so the current is discontinuous at the input side, and also from the converter the current is discontinuous at the output side also, because the inductor neither present at the input side, neither present at the or present at the output side. So inductor is present here, it is not present at the input side, it is not present at the output side. So the current ripple is high in case of buck boost converter. So whereas for boost converter, if you see, the output current ripple is high. So if you see here, in case of boost converter, so the input side, here the input side the current is continuous. So here in presence of inductor is here at the input side. So and there is a switch here and there is a diode here. So at the output side, the current is discontinuous. Okay, you can have here at the output side here for the boost converter, whereas for buck converter, the continuous output is present, but at the input side, similarly like a buck boost converter, so there is a switch here. So at the input side, you are going to have a switch, and here there is a diode, and there is a inductor at the output side. So the current is going to be continuous at the output side, but here if you see the input side here at the source side, the current is discontinuous. Current is discontinuous. So that is what with respect to the current ripple, the comparison of buck converter, boost converter and buck boost converter. So in case of buck converter, the inductor is not present at the input side, buck converter inductor is not present at the input side, therefore the current ripple is high. Whereas in case of boost converter, the current ripple is high at the output side, whereas at the buck boost converter, the current ripple is high at the both input and output side. So this is what the comparison with respect to the current ripple in case of buck converter, boost converter, and buck boost converter. So, what is the main consideration we did for the cuck converter when compared with the buck boost converter? So the cuck converter is a different circuit. Anyways, it also do buck and boost operation, but buck boost converter is already there. So why we are going for the cuck converter? So in case of cuck converter, if you see the structure of the cuck converter circuit, the inductor is present at the input. At the input side, the inductor is present, and at the output side also inductor is present. You can see the notations of L1 and L2 here. So the inductor is present here and the inductor is present at the output side. So L1 is at the input side and L2 at the output side. Due to this particular reason, you can able to have the continuous current at both input and output. So that is the main reason the cuck converter is invented. So with respect to the buck boost converter. So let us see the operation of the cuck converter. So you see here, there is an inductor L1 and there is a switch, there is a capacitor C1 and there is a diode, and again there is a L2, C2 load. So any converter, so once you see any converter, so you need to analyze with respect to the charging of the inductor, followed by the next mode, discharging of the inductor. So this is the basic thumb rule you can fix in your mind. So analyze the converter when the inductor is in charging condition. So let us name it as mode 1. So in a basic manner, so the switch is closed. When the switch is closed, inductor is going to be in charging state. So this is applicable for the basic converters, which is well cited in the literature. So when a switch is closed, the inductor is in charging condition. So analyze the converter when the inductor is in charging condition. So try to apply KVL and KCL. So check the currents and voltages. Similarly, the same thing, again analyze the converter operation when the inductor is in discharging state. So that is where you get when the switch is open. When the switch is open. Okay. So let us see the mode 1 case, what is going to happen in the mode 1. So as I said, same thing, when the switch is closed. So the inductor gets enter into charging state. You can see the inductor L1 is entering into charging state with the help of supply voltage Vs. So you can apply KVL here. Similarly, let us take L2, inductor L2. So assume that the capacitor C1 is having certain charge, because this mode is going to happen continuously. After mode 1, mode 2 happens, where the mode 2 case, the capacitor is in charging state. After mode 2, again mode 1 happens. It is repeated process. So assume that capacitor C1 is having some charge in it. So now, with the help of capacitor C1, voltage across capacitor C1, the inductor L2 is in charging state. Inductor L2 is in charging state. So this is what going to happen in the mode 1. So the inductor L1 is charging with respect to the supply voltage. The inductor L2 is charging with respect to the capacitor C1. And also it is feeding to the load. So same thing you can do for the mode 2 when the switch is open. When the switch is open, you can see interestingly, the inductor is in discharging state. It is charging the capacitor C1. So here the polarity comes positive and here negative. So the capacitor C1 enter in charging state in the mode 2 condition, where inductor L1 is in discharging state. Similarly, L2, the inductor L2 is also in discharging state and it is supplying to the load and capacitor C2. So try to apply KVL analysis first, and the same thing what we discussed for the buck converter, boost converter, buck boost converter, here also the same thing. So no need to panic with the circuit, complex circuit. By seeing the complex circuit, no need to panic. So only one thumb rule you need to keep in our mind. So analyze the circuit when the energy storage elements are in charging state, inductor. So similarly, again analyze the circuit when the inductor is in discharging state. So now let us see the mode 1 case when the inductor is in charging state. So in the mode 1, the switch is turned on. So you can apply KVL here. So when you apply KVL, VDC equal to VL1. VDC equal to VL1. The voltage across L1 comes as VDC. Similarly, you can apply KVL in this loop also. In this particular loop, the diode comes in reverse bias. Only the switch is turned on. So the diode comes in reverse bias. Why it comes in reverse bias means the capacitor voltage comes uh, to the positive voltage comes to the cathode, and the capacitor a negative voltage comes to the anode of the diode. So the diode enters in the reverse bias condition and it is in off state in the mode 1. Only the switch is turned on. So now apply the KVL in the two loops here. So when you apply in the first loop, you will be getting the voltage across L1 is equal to VDC. So similarly apply KVL in the second loop. So you can apply KVL and you can get plus VC1 minus V0 minus VL2 equal to 0. Here also the current is flowing towards this direction. So here plus, here minus. So let us take this polarity. So plus down because always current flows from higher potential to lower potential. So you can take plus here, you can take minus here. So when you apply KVL, plus VC1 minus V0 minus VL2. Again here the inductor polarities I am taking reference here, plus here minus here. The charging polarity I am taking here plus here minus. So don't change this polarity while writing for the mode 2 equation. Keep as it is. Okay. So VDC equal to VL1 is the first equation, and then plus VC1 minus V0 minus VL2 equal to 0. From this VL2 I can write it as VC1 minus V0. So let us take this as a second equation. So similarly you do for the mode 2 also, where the inductor is in discharging state, two inductors are in discharging state, and the capacitor C1 is in charging state. So let us see the mode 2. Again apply the KVL. When I turn off the switch, so the inductor current, the previous inductor current direction is in this manner. So inductor tries to maintain the current direction in the same way. So it is in discharging state now. So the KVL, if you apply here, plus VDC minus VL1. So here plus, here minus. So when I write KVL, I am taking the leaving polarity as a reference. O plus VDC minus VL1, and then here minus VC1 equal to 0. From this, the voltage across L1 is given as VDC minus VC1. VDC minus VC1. So similarly, there is a loop here, one more loop here. So the discharging of inductor L2 minus VL2. So minus VL2 minus V0 equal to 0. From this VL2 equal to minus V0. So finally, you can see there are four equations. The first two equations are with respect to mode 1. The second two equations, that is equation 3 and 4, are with respect to the mode 2. So there is a mode 1 equation and there is a mode 2 equations. Okay. So again, I said to apply to get the output voltage as a function of the input voltage and the duty cycle, definitely you need to go with the average voltage across inductors equal to 0. So here two inductors are there. So you apply the average voltage across inductor L1 separately and average voltage across inductor L2 separately. So in previous case, in case of buck converter, boost converter, buck boost converter, there is a single inductor. So we applied average voltage across inductor equal to 0 for that single inductor. But here, interestingly, there are two inductors. Here L1 is there and L2 is there. And we got L1 equation for mode 1 and L1 equation for the mode 2. So now taking these two equations, considering these two equations, apply average voltage across inductor L1 over a cycle equal to 0. So now when you apply average voltage across inductor L1 over a cycle equal to 0, I can write this equation, that is voltage across inductor L1 during on state, that is in charging state, into T on. T on I can replace as D into T. That's what we have seen in the previous video lectures. Plus the voltage across inductor L1 only during discharging state, that is switch turn off state, into T off. That T off I can replace as a 1 minus D into T whole divided by T. I can consider whole divided by T. So T get cancelled. So I can get the final equation without T. So what is the voltage across inductor L1 during on state? That is equation 1, which is given as VDC. VDC into D plus what is voltage across inductor L1 during off state, during discharging state? VDC minus VC1 into 1 minus D equal to 0. So now when I simplify this equation, I can get the voltage across C1, capacitor C1, as this manner. So VC1 equal to VDC by 1 minus T. If you observe carefully, this equation is related to boost converter equation, where you can see V naught equal to VDC by 1 minus T. VDC by 1 minus D. This relation is equal to the boost converter equation. VC1, the voltage across C1 is equal to VDC by 1 minus T. Okay, keep it side. So now the next L2 is there. So our ultimate goal is I need output voltage as a function of input and duty. So similarly, you take for the L2. So here apply average voltage across inductor L2 over a cycle is 0 by considering equation 2 and equation 4. So now write the equation, the voltage across inductor L2 during charging state into T on, that is D, plus voltage across inductor L2 during discharging state into T off, that is 1 minus D, whole divided by T. Actually T get cancelled, so here I didn't mention T here. Okay, equal to 0. So what is voltage across inductor during inductor L2 during charging state? VC1 minus V0. So substitute that, VC1 minus V0, and what is voltage across inductor L2 during discharging state? Minus V0, equation 4. So substitute that, and finally you get the output voltage is equal to VC1 into D. So interestingly, this is also you can see V0 equal to D VDC, like a buck converter, like a buck converter. So now anyways, you got VC1 with respect to inductor L1. So you substitute VC1 as VDC by 1 minus D in this final equation. You get the final output voltage in terms of input voltage and duty cycle as V0 equal to D VDC by 1 minus D. Here also you can see one interesting point here. So here plus minus. I considered plus down, minus is up. So due to that particular reason, the output voltage I am getting positive. If you take the reference polarity positive towards up, then you need to mention it as minus dVdc by 1 minus t. Minus dVdc by 1 minus t. Okay. And one more thing we need to see here carefully. So from the supply to capacitor C1, there is a boosting action. So that's what we have seen in the VC1 equation. VC1 equal to VDC by 1 minus T. There is a boosting action. And interestingly, from capacitor C1 to the load, there is a buck action from this particular equation. So this particular converter you can name also as a boost buck converter. So first there is a boosting action followed by the buck action. So you can name this converter as boost buck converter. Boost buck converter. Okay. So anyways, it does boost action. It does the buck action. When you keep the duty value greater than 0.5, it do the boost action. When you keep duty less than 0.5, it do the buck action. You can verify by substituting the duty value in this final equation. So when you keep duty 0.5, V naught equal to VDC. So this is the final output voltage equation for the converter. So what is the main goal of converter means when you compare with the buck boost converter? So it is trying to maintain the continuous current at both input side and the output side. So if you take a particular application like the supply is battery. So supply is battery. So maintaining continuous current to the battery is recommended. So that is why the inductor uh, is preferable at the source side. So for buck converter, that is the drawback in case of buck converter where the input current is not continuous. So even if you take fuel cell application, so fuel cell also recommends uh, to draw continuous current from it. So where this buck converter is going to help us to take the continuous current from the source. So that is the main motivation for the buck converter when you compare with the buck boost converter, even though the output voltage is same for the buck boost converter and the buck converter. So V naught equal to dVdC by 1 minus D. Here also the polarity is reverse when you compare with the input polarity, the load polarity is in the reverse, inverted. So that is what the output voltage equation for the buck converter. See, it is similar to the buck boost converter. Okay, now let us see with respect to the capacitor current. So here you can get some conclusions if you analyze average current through capacitor equal to 0. That is what we have seen for the buck converter, boost converter and buck boost converter. So here there are two capacitors, whereas in case of the conventional converters we are having only one capacitor. So but here you can see the capacitor C1 and capacitor C2. Similar to the inductors, you apply average current through the capacitor over a cycle equal to 0. So you can apply for the capacitor C1, you can apply for the capacitor C2. Okay, let us apply for the capacitor C2. So current through the capacitor C2 during on state into D plus current through the capacitor C2 during off state into 1 minus D. Okay, on state is with respect to the mode 1, off state is with respect to the mode 2 into 1 minus D equal to 0. This is what average current through the capacitor C2 equal to 0. Okay, let us see what is the current flowing in the capacitor C2 during on state, that is in mode 1. So in the mode 1, what is the current flowing in the capacitor C2? So IC2 I can write it as IL2 minus I naught. IL2 minus I naught. Here the inductor current comes, here IL2 comes. Okay, so here I naught comes. So when you apply KCL here, I can mention the capacitor current C2 as IL2 minus I naught. So the same thing I mentioned here. So IC2 on is equal to IL2 minus I naught. Just I substituted. Similarly, you can verify the capacitor current C2 in the mode 2 condition. In the mode 2 condition also, here the inductor L2 current flows and here the output current flows. So the capacitor current C2, I can write it as IC2 equal to IL2 minus I naught only in the mode 2 also. So if you simplify this, I am going to get IL2 minus I naught equal to 0. From this, the average inductor current is equal to load current. So from the equation itself, we are saying the average current through capacitor is equal to 0. Then definitely the average inductor current becomes output current. So IL2 equal to I naught. IL2 equal to I naught. The average inductor current IL2 equal to I naught. Similarly, you can apply average current through capacitor C1 equal to 0. So when you see the IC1 during mode 1 state. So what is the IC1 during mode 1 state? So you can see IC1 during the mode 1 state is IL2. Agree? So this IC1 is going to be like this. IC1 current flows like this. So inductor and capacitor comes in series. So interestingly, this IC1 is in the capacitor C1 is in discharging state. So this is going to be minus IL2. So let us take the charging state as a positive current and the discharging state as a negative current. So IC1 during on state, I can write it as minus IL2 into T on, that is D, plus what is the IC1 off, that is in mode 2 case. The IC1 off, I can write it as IL1. during mode 2 case, when the switch is turned off, the inductor current L1 and the capacitor current C1 both are same. So I can write IC1 off as IL1 only. So now you know IL2 already. So when you substitute IL2 here, minus I0 into D plus IL1 into 1 minus D, I can get the average inductor current L1 as I0 into D by 1 minus D. IL1 average as I0 into D by 1 minus D. Okay, let us see the input power. Input power is input voltage multiplied with input current. Input voltage is multiplied with the input current. What is the input current here? IL1 only. The inductor current IL1 is same as input current, average current. So I can substitute here IL1 in place of IN. So Vin into I0 D by 1 minus D. So I can take I0 out. So Vin into D by 1 minus D. Again, here Vin, VDC both are same input voltage. So I can take it as V0. So from this, I can make a relation input power is equal to output power. Since I didn't consider any non-idealities in the analysis, I can arrive this equation as the input supply power is equal to the output power consumed at the load. Okay, so now come to the waveforms. So if you understand the analysis, the waveforms are very easier. So no need to by heart here. So I started with the gate pulses even for any converter. So it is recommended to start with the gate pulse of the prime switch. Okay, whichever the switch you turn on as a prime switch. So you start with the gate pulse, drawing the gate pulse. So when you provide gate pulse to the main switch or prime switch, the inductor L1 and L2 both are in charging state. Okay, so after drawing the gate pulse, try to mention the inductor currents, because the remaining elements currents, the remaining element currents, that may be a diode current or switch current or capacitor current, it follows the inductor current nature. So it is always recommended to draw first inductor currents. Okay, when the switch is turned on, inductor is in charging state L1. Okay, and similarly for the inductor L2, both inductors are in charging state. Both inductors are in charging state. So what is the current flowing in the switch? It is sum of IL1 and IL2. Sum of IL1 and IL2. That is, both are in charging state. So that's why we made the a rising slope of the current. And what about the voltage across the switch? As the switch is turned on, approximately you can make voltage across the switch as 0. And what is the voltage across the diode? So when the switch is turned on, the diode becomes reverse bias. Why it becomes reverse bias? The capacitor voltage apply across the diode. The reverse voltage apply across the diode with the capacitor voltage. Okay, so that is what you can have the voltage across the diode as minus VC1. It is going to block the reverse voltage. And already you know what is VC1, VDC by 1 minus T. So when you select the diode, okay, you ensure that so the voltage of the diode, the breakdown voltage of the diode should be greater than VDC by 1 minus T. Okay, so similarly, what is the current through the diode? In this particular mode 1 case, as the diode is in off state, there is no current flowing in the diode. And what is the current flowing in the capacitor C1? So it follows the inductor current IL2. It follows the inductor current IL2. Whereas here inductor current is in rising state. Already we mentioned that the discharging of the capacitor is seen in the mode 1. So the discharging, I can mention it as a negative polarity. So the IC2, the IC1 comes to be a negative side with a rising slope, IL2. It follows IL2 because the IL2 and C1 comes in series in the mode 1. Okay, so the IC1 current follows IL2. IC1 current follows IL2. Okay, so this is what with respect to the mode 1 of the Cuck converter. Mode 1 of the Cuck converter. So similarly, you analyze when the gate pulse is removed. when the switch is turned off. When the switch is turned off, the inductor L1 is discharging state. Okay, the inductor is L1 is in discharging state and charging the capacitor C1. So the same line can be drawn for the capacitor C1 current, capacitor C1 current. Okay, so this is how you can draw IC1 and then IL1. What about IL2? IL2 is also in discharging state. Through which device? Through the diode. Diode comes in conduction in the mode 2. So the IL2 current flows in the diode. So you can draw the diode current the same in the same manner of IL2, and interestingly IL1 also flows in the diode. So it is sum of IL1 plus IL2. IL1 plus IL2. What about the switch current? When the switch is turned off, the switch current becomes 0. And what is voltage across the switch? The voltage across the switch is going to be VC1. It is blocking the VC1 voltage. You can observe here. Once the diode gets turned on, the VC1 voltage comes across the switch. So the VC1 is given as VDC by 1 minus D. So it is blocking the forward voltage of VDC by 1 minus D. This is how you can analyze the model graphs for the Buck converter. And what about the capacitor C2 current? So you observe that the capacitor C2 current is IL2 minus I0. IL2 minus I0. So IL2 average is I0. So that's what we derived in the in this slide. Particularly in this slide, we derived that IL2 average is equal to I0. So now you can draw the capacitor current IC2 by seeing this. So I0 average, IL2 average comes I0 exactly in the middle. So whenever there is an intersection of IL2 and I0, that point IC2 becomes 0. So in this particular region, I0 is greater than IL2. That's why the capacitor current is in negative. So after this, in this particular region, IL2 is greater than I0. That's why the IC2 current comes in the positive. So again, there is an intersection here, IL2 equal to I0. Here at this particular point, IC2 equal to 0. So this is how you can draw for the capacitor current C2. Capacitor current C2. These are the model waveforms for the Buck converter. Model waveforms for the Buck converter. So now coming to the design of elements. So here, how many elements are there? So you need to design value of L1, value of L2, C1, C2. So how to design these passive components L1, L2, C1, C2. So in the previous videos itself, I mentioned to design values of inductor, you need to look into the KVL equation and get del I. Because the inductor design is based on the ripple current del I. Whereas to design the values of capacitor, I mentioned look into the capacitor current and get del V, ripple voltage across the capacitor. Ripple voltage across the capacitor. So there is only one thumb rule here. So when you design inductor L1, so you need to look into del I, inductor ripple current del I. So this del I comes from the KVL equation of the inductor. So you get VL just by applying KVL equation. That is what we have seen in the mode 1, mode 2. Okay, so you can use the same formulas and get the VL and get del I. Similarly, to design capacitors, see the capacitor currents. From the capacitor currents, you can get del V, the ripple voltage across the capacitor. So that is what we'll see in the coming slide now. So design of Buck converter, passive elements L1, L2. Whereas active elements, you can check the voltage across the each element. So you choose the blocking voltage of these element greater than the values which you arrive, VDC by 1 minus T. So greater than this you can choose. And also current. You can choose the current which is greater than IL1 plus IL2. Okay, so IL1 average you can check here and IL2 average you can check. So choose the active component current rating. The summation of these two, it should be the element should be capable of withstanding at least the IL1 plus IL2 average. Okay. Now come to the passive components. So that's what I said. So to design values of these L1 and L2 inductor, so you need to consider del I. So where this del I comes from the KVL equation, get VL. So if you check with the mode 1 case, mode 1. So we mentioned in the mode 1, the voltage across inductor L1 is equal to VDC. The voltage across inductor L1 is equal to VDC. That is what we mentioned in the mode 1. So VDC equal to VL1. So from this, I can write VL1 as L del I by del T. So from this del I can write it as VDC D by LF. This del T, I can replace it as D into T because this is the mode 1 equation. During on time, I am checking what is the ripple current del I. So you can check, you can take for mode 2 also. You can take for mode 2 also. Both comes same only. There is no deviation. Both the L1 design equation comes similar. Okay. So from this L1 I am getting as VDC D by del I1 into F. So user is going to specify what is the required permissible inductor ripple current del I1. So you substitute VDC, you substitute D duty, you substitute switching frequency, you substitute del I1, you will be getting the design value of L1. Similarly, you can check for the L2 with the help of del I. So how to get del I? Again, applying the KVL equation. So in the mode 1, we arrived VL2 as VC1 minus V0. That is what we have seen in the previous slide here. In the mode 1, VL2 is equal to VC1 minus V0. Same thing I mentioned here. So what is VC1? We arrived in the previous slide, VDC by 1 minus D. So finally, I'm bringing in terms of input voltage. Okay. So VL2 is also equal to VDC here. VL2 is also equal to VL2 is equal to VDC. Again, VL2 equal to L2 into del I by del T. So from this, I can write L2 as, so this del T I can write it as D into T. So I can write L2 as VDC D. This T comes to the denominator, it becomes F, switching frequency. So L2 is equal to VDC D by del I2 into F. Del I2 into F. This is how you can design the values of L1 and L2 for the CUC converter. User is going to provide you what is VDC required, what is the input voltage, and what is the duty, what is the switching frequency, what is the permissible ripple current, inductor ripple current. So substitute all these parameters to design the values of L1 and L2. So this is how you can design the passive elements L1 and L2. Come to the capacitor. So how to design the capacitors? By seeing the current through the capacitor. So again, by seeing the current through the capacitor, you can arrive del V, the ripple voltage across the capacitor. So this also you can consider any mode, either mode 1 or mode 2. So I am considering mode 1 only here. So in case of mode 1, IC1 equal to I0, average inductor current that is I0 only. So IC1 equal to I0. Okay. So how I can write IC1 C into dv by dt, del v by del t. Again, del t I can replace it as d into t. So from this I can get del v. So from this equation I can get C1 as V naught d divided by del v into R into F. So V naught user specify, duty is also going to be specified by user, del v load resistance, it is known to us, switching frequency also known to us. So you can design the value of capacitor C1 to maintain the del V, to maintain the particular ripple voltage across the capacitor C1. So come to the capacitor C2. If you see the capacitor C2 current, so it looks similar to the buck converter capacitor current. So you just recollect buck converter capacitor current. So it is similar. So from this, I can get del Q as area under the triangle of into. So this current is with respect to the inductor L2. So that is del IL2, peak to peak ripple current del IL2 divided by 2 into T by 2. So this time is given by T by 2. T by 2. So from this I can get 1 by 8 into del IL2 into T. So that is what del Q. Del Q. Okay. So del IL2 is already known to us. Del IL2, what we can write here? Del IL2. This is del IL2. So VDC D by L2 into F into T. So del IL2 I substituted VDC D by L2 into F into T. So now this change in Q, del Q you substitute in the del V equation. So you will be getting the final C2 capacitor C2 design. So the only thumb rule here also, to design capacitor C2 you need to check the capacitor current. From the capacitor current you will be getting the del V. Del V. So this is how you can design the passive components for the converter, that may be inductor or capacitor. So this method remains same for any converter. So with this I'm going to stop the session. Thank you very much. If you are having any doubt, you can feel free to contact to my number. So I request everyone, those who are seeing this video lecture, so you can join in the WhatsApp group for further clarifications required. Thank you very much.